Hi, everybody. Welcome to today's webinar. Are we good to go? Basics of Acceptance Sampling Plans. My name's Elaine Eisenbeisz. I'm the owner and principal statistician here at Omega Statistics. I will let you know early on, I was planning on doing attribute sampling plans and variable sampling plans, but it got way too unwieldy. So what we'll do is we'll do the attributes today. And then I scheduled a webinar for next month. I think it's February 16th. And then we will go ahead and do variable sampling plans then. Okay, all right, well, let's get started then. Like I said, thank you for those of you who took the time to join us live today. And as I was saying, today I'm going to present an overview of acceptance sampling plans for attributes data. And as I said, I wanted to cover both attributes and variables sampling plans, but just too much information for one 90-minute webinar. And so I'll sign everybody up for next month. And if you don't attend, that's fine. You don't have to go live. I'll still send a recording and handout like I always do. Today's just an overview, but as always, I hope that the information you receive today will give you some ideas and guidance towards further understanding your statistical findings and how to work the statistics. And as I say in all of our webinars, use what you learned today, apply it in a holistic way, look at that big picture. You can read some information here about Omega Statistics. I won't go through everything. Oh, you do have some handouts. If you want to look in the handout area, I put the slides in there. I also put in a list of definitions. There's so many definitions today. I even have to look at them sometimes, so many acronyms. And then we're going to do a sampling plan. We're basically going to stick to simple sampling plans today. I'll also show you a zero acceptance sampling plan. But I do have a description, a Word document with a description of how to read that output in Minitab. I'm going to go through it, but rather than you write a lot of notes, you can go ahead and use that handout. And then, as you do your sampling plans, just, you'll use different numbers, but the definitions will be there for you. Okay. So this is about me here. I do clinical research, a lot of that, mostly. Some analytical validation also. Of course, I do process and quality control, obviously. I do design, analysis, I generate reports, all these acronyms, and I help with dissertations. And our motto is to provide elegant solutions effectively applied. Okay, so for today, we're going to look at just fundamental concepts of acceptance sampling. We're not going to get too detailed, but I think it'll be a good start. It's a good overview, and most of my webinars are overviews, right? But they're very useful. We'll look at some OC curves. We'll look at some the quality indices, the AQL, the LQ, also called LTPD, RQL. Oh my gosh, so many acronyms. Okay, so we'll go through those, and then we're going to look at sampling by attributes. We'll look at single sampling plans. We'll look at the C=0 or the zero defect sampling plans. And we'll also take a look at the ANSI tables, the ASQ tables, the Z1.4. I don't have the actual tables today. They are proprietary. You need to purchase them. However, they're based on a military standard from long, long ago. In fact, it's still typewritten. Yeah, so at the end, I have in the reference section a link that you can go and get those military standards. But you'll see when we get to those pages, they're not very pretty. And the standard itself is not very pretty, but we'll do our best with it. Okay. However, the ANSI and the Z1.4 are based exactly on the military standard, so it'll be useful for you. And then we're going to talk about these. I'll show you a slide or two about double sampling plans, multiple sampling plans, sequential, and skip lot sampling plans. But we won't go into those too much today. Double sampling plans can be useful, but I think these other three right here, it makes my brain explode. I mean, it's just sometimes I think, especially statisticians, we do, especially now when we have computers and such and all these capabilities, sometimes we make things harder than they need to be. A single sampling plan usually will serve you very well for the most part. Okay, so why not 100% inspection, right? Why don't we look at everything? Well, it's pretty obvious why. You know, we can't do it. What if it destroys things, right? If we're say looking at light bulbs, one of my favorites is light bulbs in a lot. Well, if we're inspecting their burnout times, we can't burn them all out, right? Then we won't have anything for the consumer. We won't have anything to sell. And of course, there's large costs in time and money, even if you don't destroy. And we also, a lot of the handling, right? Maybe some of the handling just to inspect things could result in some defective products. So typically 100% inspection would only be done when any defective items would cause big problems, when you have very, very high risk or something that's defective is really going to hurt somebody. Right. And there are different risk levels. And as we know in process and quality control and quality management, it is very much based on risk levels. Okay. So what we're going to do is we're going to use acceptance sampling instead. We're going to look at the lot of product, but we're not going to look at everything. We'll pull a sample, will allow us so many defectives, and if it's under a certain margin or a certain acceptable quality limit, then we will say, okay, lot's good to go. If it's higher, then unfortunately we have to replace the defective items and look at everything in the lot. So that's typically how it's done. Okay, so here's some reasoning. As I was saying, it's not done to measure the quality of the entire lot, but only to decide if that lot is acceptable or not. So basically, you're going to accept or reject the whole lot of product based on what you find from your sampling. Okay, so we can use it to determine a quality level of an incoming shipment. We can use it to judge whether the quality levels within a predetermined level set by the company, the manufacturer, the producer, or the consumer, the people, the end users, you know, who are receiving the product. It doesn't give any information about the process that was used to produce the items. Since we're not looking at each item in the lot, we do have some risk, right? Good product could be rejected. Bad product could be accepted. We're only looking at a sample. We're not looking at everything. So it is possible that you know, we could be sending out a bad lot. However, random sampling is a big deal. If we choose randomly from the lot, don't choose the first 10 or 20 things in the lot, right? Because maybe coming off the line, something happened there. If we randomly sample, then it's going to help us control for any kind of variability that's in the product. And there's always variability. We don't have 1,000 of the same thing exactly the same. There's going to be little variability, but that random sampling will help. And it's easy to find random sampling schemas. You can do it in our software. I think you could probably even do it in Minitab. I'm pretty sure you can, but Excel, there's a lot of ways to do it. I'm not going to go into it today, but I do want you to keep in mind that it needs to be a random sample. So I have here, what is acceptance sampling? Let's see if I can find my little marker here. Here's my spotlight. Good. Okay. So it's a statistical quality control technique, of course. Again, random sample. It needs to be random. Don't take the first 10, 20, 50, whatever. The sample is investigated for non-conforming items or defectives, okay? And this is acceptance sampling based on attributes today. So we're just going to look at things that are defective or not. So go, no go kind of things. Variable sampling, which we'll look at next month, is going to look at measurements or acceptance based on things that are a continuous type of variable, like weight or you know, size or tensile strength, things like that. But today it's just, is the product effective or not? You know, is it good enough to ship or not? Okay. And so based on our sample findings, we're either going to accept or reject the entire lot of product. Okay. And I have right here the most widely used sampling plans for attributes are based on that military standard. The standard was discontinued in 1995. And we went to this instead, but this new military standard was issued in 96, and it's based on the C equals 0, the zero acceptance sampling concept. But many people will still use this Z1.4, and then for variable sampling plans, we're going to have the Z1.9. I do have a note here that some people think that because that standard 105E was discontinued, that the concepts and application of the statistical theory in them is no longer valid. And that's not true. Statistical theory builds, I mean, it holds up regardless of the cancellation of a standard. So the Z14 is still widely used, but it's based on that 105E, and then that military standard, the 1916, is the same as the C0 sampling plan by Squiglia, Squeglia. I've never pronounced it right, and we'll look at that in a little bit. And that, if you can look up the Squiglia sampling plan, it's a pretty easy read, just a few pages, and very useful. I don't care much for the zero defect C equals zero sampling plans, and I'll tell you why in a little bit. But a lot of people like to use it. They think it's beneficial. I think there's drawbacks. All right, time for terminology. So we have acceptable quality level. It used to mean acceptable quality limit, and I think I still say that, but the ANSI and ASQ Standards Organization changed the term to be acceptable quality level in 2008. I'm not sure why, but it means the same thing. Okay, it's the maximum number of defective goods that you can have before you go ahead and reject the lot. And it's usually defined as a % defective, okay? And we'll have a probability of acceptance here. 95% is usually the standard. In the medical device industry, common AQLs are going to be 0.4, 0.65, 1%. Okay, in pharmaceuticals, it's sometimes a little bit lower. It's 0.25%, 0.4%, and 0.65%. Those are the usual standards. But in both industries, there's often a spec AQL, and that's typically 1% defective. And lots below that spec AQL are released, and lots above it are rejected. However, the spec AQLs are not to be used as a way to provide permission to make defects, right? And we should strive for 100% acceptance, acceptable in all of our processes. However, if there's only one defective in a sample of 100, it doesn't make sense to reject the entire lot or do 100% inspection of the items. The cost is too great to the producer and the consumer. Okay, the AQL is defined by both the producer and consumer prior to any pre-shipment inspection. It also, defects and defectives are also defined by both parties. So I have an example here. If we have an AQL of 1.5%, which is kind of rather high for if you're in medical or pharmaceutical, but that's what I use today in most of the examples. If we have an AQL of 1.5 and an alpha of 5%, then that's going to we would expect to accept lots that had 1.5% defective 95% of the time. Okay, so the alpha 5% is the same as the 95%. If you take 1 minus 5%, that's where you get the 95%. And apologies if I'm being a little too simplistic here, but sometimes people come to the webinars and they really, don't really have that basic understanding. So sometimes I define things a little much, but I'd rather do that than not enough, right? Okay, so some more terminology. We have the LQ, and that's defined by the consumer. So therefore can vary much more than the AQL, because, producers going, okay, we want to ship this out if it's, below this certain limit, and we're fine. But the consumer, they might be able to accept more risk. And so they could be, it's a little more leeway there and a little bit, more variable, okay? And the LQ depends on past performance, time to process has been in service, other controls in the process, types of failures. Different manufacturing plants can also have different LQ values, okay? So it's the quality level that's unacceptable to the consumer. We have beta now, and that's the probability of committing something called the type 2 error, and that's the risk of accepting a bad lot, okay? And it protects that consumer from accepting the bad lots, and the common value is 10%, and you'll often see the little beta down here, and so in this case you'll have LQ10. You might see LTPD10, right, or RQL10. All these mean the same thing, and I think today I talk about RQL a lot. It's kind of like an older way of saying it, but they're all the same thing. And I always joke that statisticians like to have 5 names for everything. Typically, that happens because we work in so many different industries, and statistics is applied across so many disciplines, and every discipline has their way of saying things. So just make a note of that. If you get confused, let me know, and I'll try to. Hopefully, I won't get confused too, right? Here's an example here. If we have an LQ, oil TPD RQL of 7.5 and the beta is 10%, that's our probability of, risk of accepting a bad lot, then we would expect to reject lots that have 7.5% defective units 90% of the time. Okay. Again, that beta is just 1 minus beta because 1's 100%, right? So 1 minus 0.10 is 9.90, which is 90%. I also say think of it as accepting these lots only 10% of the time if they have the 7.5 defective units or more. Then we have consumer's risk versus producer's risk, and this is the alpha and the beta here. Okay, this is the producer's risk is the alpha. Usually that's the 0.05. Represents the likelihood that a given lot whose defect or defective rate is equal to the AQL. It will be improperly rejected. So the higher the alpha, the more likely acceptable lots will be rejected. And that's going to cause harm to the producer because we're going to say they're not, we're going to reject them when they were perfectly, good enough. Okay. And the beta is kind of the other way around. That's the consumer's risk. It's not really the other way around. This is for the producer and this is for the consumer. Okay. And for the consumer, it represents the likelihood that a given lot whose defect or defective rate is equal to those LQ, LTP, RQL. It'll be found acceptable. So the higher the beta, the more likely rejectable lots will be accepted. Okay. So we're going to be taking bad lots. Okay. Then we have other terms. Sample size is usually this little n. The lot size is usually big N. So you're going to take a little n from the big N. Okay. Acceptance number, sometimes you'll see this as an A. Quite often nowadays you'll see it as a C. So I think in the slides I do have one point where it's an A. But the maximum number of defects or defectives that can be found and still allow the lot to be accepted. So if I have a C equals 3, I would accept that lot if it has 3 or fewer defectives and reject it if it has 4 or more. So we're allowed up to the C number. So I could have 3 and still pass that lot, but if it's above 3, then we can't do it. And here we are dealing with just items. It's attributes, so we're not going to have anything like 3.5 or 4.2 or anything like that. We'll see that next month. So these are just 1, 2, 3, 4, just numbers. Because it's go, no go. Defects and defectives too is just something that's interesting. Defects, you could have defects and that's still okay sometimes. Defectives is what you're really looking for. But sometimes a defect might cause you that's rejectable. Okay, so it really depends on what you're looking at, what your organization's doing, what you're manufacturing. But a lot of times maybe you have like a little scratch or something on the bottle. Well, that's a defect, but you're not going to say that the product inside the bottle's no good, right? It's just got a little scratch. Maybe if the label's torn, that might be a problem, So that's something that your organization, wherever you work, will decide what is considered really defective. But sometimes defects are okay. It's the defectives that are the problem. Okay, then we have rectifying inspection, and that happens whenever you don't accept your lot. You have to reject a lot, and when you do this for a rectifying inspection, all the defective units have to be removed and replaced, of course, with compliant product, and you have to do 100% inspection on the lot. And so that's the problem with sampling. Sometimes if you reject a lot, then you end up doing the 100% inspection anyway. We also have the average outgoing quality, and that's the expected outgoing quality of a lot of a given incoming quality after rectifying inspection. We'll do some charts and I'll show you this. This is over time. Okay, so over time with your sampling plan, you're going to have some kind of number for average outgoing quality. Average outgoing quality limit is the worst case average outgoing quality you'll have, and that's specified at the incoming quality that after rectifying inspection results in the maximum AOQ. And again, these are a lot of words, but when I show you an example, I think it'll make more sense. And then we have the average total inspection, and that's the expected number of units inspected, assuming rectifying inspection. And expected, whenever you see things like it's expected, that's basically over long range, over time. You'll see expected value, long-term odds, things like that. Well, that's like over and over and over. This is how much you would expect to find defective lot per lot over a long period of time. So we'll look at that a little bit more. Okay, but we really need both. Oh, I was going to tell you too, please excuse the slides today. I had them all nice and pretty, but gosh darn it, yesterday about 4:30, I was tidying them up and I don't know what I did, so they're pretty boring today. But the information's there, right? So anyway, we really need both the AQL and the LQ. Okay, many people wrongly believe that lots with percent defective above the AQL will always be rejected, and that's not true. We're working with a random sample, right? And we're working with probability. We're working with statistics and probability. So we always have that wiggle room. We always have some leeway. So to select a statistically valid sampling plan, first, the objective of the inspection should be determined based on past performance, maybe other controls that are in place, potential failure modes, and so on and so on. You could probably think of some other things, right? Then you'll have the AQL and the LQ of the sampling plan should be documented. We document everything, right, to determine that the sampling plan meets the objectives, okay? And then further, since different sampling plans may be statistically valid at different times during the life of a process, all sampling plans should be periodically reviewed, okay? So you want to have a schedule of review for them. If you don't know the protection provided by your sampling plans, a good first step is to document all of your sampling plans, AQLs and LQs, LTPDs, RQLs, right? To document those two things. Then for each sampling plan, you should ask, is this protection appropriate based on past performance and current controls? Sometimes a process changes, right? Or maybe there's something, maybe the machinery was updated. Maybe one of the machines is malfunctioning. So once you set these plans for process and quality into place, you do need to look at them on not a continual basis, maybe at first, but it really depends on the length of your processes, what the risk is for sending out bad things, and there's so much more involved, right? And that's why I say look at things holistically. So I have here, it's a good idea to generate sampling plans based on both the AQL and the LQ. You need them both, okay? And that's what we'll do today. Okay, so let's look, I think it's good to look first at this operating characteristic curve. Do we have any questions? I'll look really quick here. Oh, it looks like we might have a question here. Oh, Kalinzi asked, does handling defects relate to people as well? If you're sampling, I would say yes. Say you were doing that, I don't know if you meant that to be funny, but it kind of is. But really, seriously, if you, probably not in this kind of, if we're doing with pharmaceutical or medical devices. However, if you're doing a survey and maybe a study in the social sciences or something like that, I wouldn't necessarily say defective people, but maybe some of the surveys are bad, right? And you would set some standards on what would be considered a defective survey, and you wouldn't include those in your analysis. So yes, yeah, I guess so. I don't know if we would set up something like this for it, but there would be some criteria for it. That's pretty cute. Okay, operating characteristic curve. So I'll go through this really quick. The OC curve for a sampling plan quantifies the sampling risk graphically, right? So you're going to plot the probability of acceptance, which is the P it's usually P with a lowercase a, right? Or P, and that's going to be here on the y-axis, okay, of a lot. Okay, so this will be, for lots, as a function of the lot percent defective, and that's going to be down here on the x-axis. Okay, so these are probabilities, go from 0 to 1, which is 0 to 100%. Basically, and the percent, these are like 1%, 2%. These are not items defective, these are percent defectives. I mean, once you get up to 10% defective, do you really want to send that lot out, right? When the percent defective's high, we want the probability acceptance to be low, right? So here we have our percent defective at 10%. So our probability, is getting very close to 0 for accepting that lot, and vice versa. When our percent defectives are low, which are down here, maybe they're under 1%, and we're going to be accepting almost 100% here, right? No defects, you'll have 100% acceptance. Okay, the behavior of a sampling plan is described by the sampling plan's operating characteristic curve, which is this. Okay, so this figure shows the OC curve of a single sampling plan. The sample size is 50, and the acceptance number is just 1. Okay, so if we have 1 defective out of 50, we're going to reject. Well, 1's okay if we have more than 1. So if we have 2 or more, we'll reject. Okay, and then the x-axis, as I was saying, it gives different process percent defectives, and the y-axis axis has that corresponding probability of acceptance. So, for example, find 3 on the bottom axis, so that's 3% defective. Then we'll draw a line up to the curve, and we'll go over to the y-axis, and the number's 0.56. You can't see it, but that's what it would be. Okay, so the probability of acceptance would be a little bit over half, about 0.56, 56%, when you have 3 that are defective. Okay, so it is possible that you could have more than defective than your AQL is allowing you to, and still maybe a little over half the time still be accepting that lot. And let's see, so if we also have a probability of accepting 1% defective lots, say we go up to about here, 1% I have is about 0.91. Probability of accepting 7% right here is about 0.13 or so. This is a little bit high, actually. This is my LP. This is what the consumer wanted. They're saying, okay, if it's over 7.6, I'm not interested, right? Don't want it. So at this, it's 0.13. Okay, is our probability of acceptance. So that's good for the consumer. If it's over that, we're going, okay, if it's over that, then, they're pretty much not going to get their bad lot. And then right here is our AQL. This is what the producer set. We're not going to release this lot unless it's this or under. And then, so we'll be releasing it about 91% of the time. So that's pretty good. But there's a lot of wiggle room in there, right? OC curves are generally summarized by 2 numbers, as we were saying, the AQL and that LTPD, which is also, what is it, the RQL, and the other one. See, I'm even forgetting, but there's 3 of them. So the AQL, that's at the percent defective with a 95% chance of acceptance. That's what we said on this one. And that LTPD is that percent defective with a 10% chance of acceptance, which those are your alphas and betas, right? And so at the LTPD, 90% of the lots should be rejected. And that's about right, 0.13. That's pretty good, 1 minus 0.13. That's pretty close. So I have some notes here that what protection does the single sampling plan of sampling 50 with allowing for 1 defective provide? Well, since sampling plans make accept reject decisions as far as attributes plans, this question is best answered in terms of what the sampling plan accepts and what it rejects. So the AQL describes what a sampling plan will accept. Lots at or below this 0.72% defective are routinely accepted, okay? And that means at least 95% of the time, okay? That's how we set it. And the LTPD describes what sampling plan rejects. So lots at or above this 7.6% defective are routinely rejected again. Okay, we have that 0.13. So at least 90% of the time is what we set. Okay, we made that beta of 0.1, 10%. Okay, so as I was saying, lots between the AQL and this LTPD, all in this area of the curve. They're sometimes accepted and they're sometimes rejected. And depending on what number we have down here is the percentage, the probability, okay? And then I have a note here that you should document the AQLs and LTPDs of all of your sampling plans, of course, also your alphas and betas, right? The AQLs and the LTPDs of the military standard that we'll look at, and the ANSI, the Z14 sampling plans can be determined using tables. There's 3 tables that you kind of have to look through. One table tells you information to put in the next table. It tells you information to put in the third table. And you don't really need those for that, but you do need some probabilities of acceptance and such. And we can use Minitab, which we will be doing today. And I'm still saying we still need those AQL and the LQ, at least for what we're doing in Minitab and such. Here we have some comparisons of sampling plans, and I'll show you how to do this in Minitab. But in order to understand the level of protection provided by a sampling plan, you should know what the plan routinely accepts, right? That's that AQL. And what it routinely rejects, which is that LQ. That's the other one I was thinking of, LQ, LTPD, RQL. Okay. So remember, AQL is that producer's risk of wrongly rejecting a good lot, and that LQ is the consumer's risk of wrongly accepting a bad lot. And this IQL here is a difference, it's called the indifference quality limit, where a lot has an equal chance of being accepted or rejected. That's that 50-50 area. And this is what we call the sampling plan's blind spot right here. So here's our different plans here. If we sample 132, I don't have here how big the lot is, but I guess it doesn't really matter for this, but you know, it will kind of matter when we do our sampling plan. But here we're taking a sample of 132. We're allowing 3 or less, okay, to be defective. And here's our AQL. And that was based on this AQL and based on this LQ, and then so on with the different plans. But as you can see, we have right here, these AQLs are pretty much the same for the producer. And the LQ, though, really changes depending on how you're sampling. Okay, look right here, the risk goes way, way up. I mean, this is, you're asking the consumer to accept about 14%, up to 14% effective. Nobody wants to do that. So how many you're sampling, the sample size, and how many defectives you're allowing for really does make a difference. Not so much on the AQL, but really on this, the consumer's risk. These are all the LQ10, so very interesting. And these different curves here show you the different sampling plans over time, percent defectives, and the probability of acceptance. It looks like right here, the blue plan, the one is 132, and you're choosing 3. It kind of has a much steeper curve here, and you're going to be rejecting a lot faster than you would with the 25 and 1. You're only having a sample of 21 and 25 in your sample, and allowing for 1 defective, and it kind of goes a little bit. And this is where the consumer's risk is much higher, because you're allowing yourself to send it off a lot longer than you are with this one here in the blue, which is the 132 and the 3. Okay. Let's see, I do have some questions here. Charles wanted to know, does double sampling, is it the same as multi-stage? It's not. Multi-stage is a little more difficult. So we will go over that in a little bit. And let's see, if the percentage is 50-50, Charles also wanted to know, does it require a second opinion or not, since it's half? Well, it's 50, it's basically over time, right? So you might be sometimes sending out bad lots, because remember, you're just going to be sampling. You're not looking at the whole lot, right? The only time you'll be looking at the whole lot is when you reject. So there might be times when, even though we're randomly sampling, okay, we are randomly, as long as you pull that random sample, it's supposed to help control for this. But maybe you still do get lucky. We're only allowing like a 95%. That means 5% of the time you could just get lucky and pull a really good sample out of that lot, and there's defectives hidden in there. You just didn't pull them, right? So it's basically that 50-50 and such, and that blind spot is for lots over time, not individual lots. You never really know, because you're not really sampling the whole lot. You know, you're just pulling a sample from it, unless, of course, you're doing 100% sampling if you reject. Does that make sense, Charles? It's all about probabilities. You have to kind of think like a statistician, and that's really hard. It's like I always say, sometimes we just everything's one of our biggest things are saying it depends. It depends. Because we don't know the truth. If you knew the truth, you wouldn't need statistics, right? If you sampled your lots 100%, you would know. But that 50-50, sometimes your bad lots will go out. Sometimes good lots will go out, So yeah, that's the drawback. Okay. So let's go ahead and look at the basics of designing a sampling plan. What we want to do is select a plan for a specific curve. So when we select the plan, it'll give us the curve in Minitab. We're going to specify our AQL. Here I called it an RQL, right? But that's that LQ, LTPD. We want our alpha, usually it's 0.05, and our beta is usually 0.1, right? We need to know our lot size. How big is our lot, right, that we're sampling from? Okay. And the output is going to be given to us from the sampling pen. It's going to tell us what the sample size is and the number of defectives we're allowed to have. And if we're doing a rectifying inspection, of course, we're going to have 100%. That's our big N. Big N is our lot size. And then we're also going to have these AOQL and the ATI also provided. And these are going to be averages over time. And they look really confusing when you first see them because you're going, well, wait a minute, it's the lot size on 100%. If we have a lot size of 5,000, how come my ATI is 4,900? It's not 5,000. It's over time. Okay. Or our AOQL, or samples. So then I'll show you in a little bit here. Then we're going to take our plan. We're going to expect the sample of whatever size we got from the lot. And then we'll accept if the number of defectives is less than or equal to RC, and we're going to reject if it's above. So we can have up to C and still accept. Okay. So the big question is, well, how do you know what values to choose? Well, for the LQs, for validating new processes or process changes, they should be smaller than for regular manufacturing with mature processes. Okay. And it depends on the severity too of a failure. Do you have critical, major, minor, cosmetic? Your company's quality engineering standards should have target quality levels based on severity. And the main driver should always be protection of your end user, your consumers, your patients. If we're in the medical or pharmaceutical, right, we definitely want to have the patient safety. So yeah, when you have a new process, you might want to bring this down a little bit, right, for your LQs, because you're not really sure yet how good those batches are, how good those lots are, right? And so it's definitely state your claim. So if you want to say at a 95% confidence that the percent defective for each lot should be less than or equal to 1%, then I'm going to design a sampling plan with an LQ5 of less than or equal to 1%. Okay. And if I want to say 95% confidence, the percent defective for each lot should be less than or equal to 5%, then I'm going to have my LQ10 at less than or equal to 5%. Okay. So things like that. So kind of state your claim, that'll help you. Okay, so again, we have the sampling plans by attributes and variables. The kind of data you have will determine whether you use attribute or a variables plan. And today we're doing attribute. It's the simplest kind. Boy, wait till next month. I'll try to be as good as I can with it, but even it wraps around in my brain a little bit. And you sample some number of items and you classify each item as either having a defect, it's defective or not, it's useful or not, you can use it or not, and you'll have some standard for what that defective item is, like broken, scratched, non-functional, right? When your data points are measurements on a numerical scale, then you have variables data. So if you're measuring something that, I always say if you have decimal points, if you're measuring something that has decimal points, then you're using a variable sampling plan. So like weight, diameter, tensile strength, things like that, you can have decimal points, right? You could have a weight of 12.6 ounces, right? But if you're measuring things that are units, like 1, 2, 3, 4 items, you know, they're either go, no go, defective or not, than your attributes. Okay. And variables data does contain more information, and it allows you to use a smaller sample size. And it allows you to assess things like how much, how bad, how good, rather than just yes, it's defective or no, it's not. Okay. And because variable data contain more information for each data point than the attribute data, variable sampling plans require fewer samples than the attribute sampling plans for the same level of protection. We'll see that next month. And this translates into lower material costs, less work, less time. Okay, but it's particularly wasteful of information and materials and work and time when people go to the trouble of taking measurements on variables data and then compare each data point to a specification limit and treat them as good or bad, or in or out, right? Or go, no go. Okay. So don't change your variables data into attributes data. So next month we'll show you how to do the variables. Okay. Because whenever you do that converting to yes or no, it downgrades information-rich variables into like sparse attribute data. And a sampling plan that uses go, no go data should really be used on that kind of information. Okay. And I think that's about all I have to say on that. So let's go on and look at the attribute sampling plans. Okay. So here's a basic way to do it. First, you need to know the lot size. Then you need to specify the sample size, and then the acceptance number, which is the maximum number of non-conforming units allowed. And if it's greater, then we're going to reject that lot, and then we're going to run the test and make your decision. And if the lot's rejected, decide on the course of action you'll take next. And usually that's the rectifying inspection, where you replace all the defects that you found, and you go through and look at 100%. And as you're going through and looking at them, as you find more defectives, of course, you're going to replace those too, until you've looked at them all and nothing in there is defective anymore. Okay, so this is the simplest one, the single sampling plan. It's the most common. It's probably answers most of the questions you'll ever have about sampling for attributes, the go, no go kind of yes, no things. It's more product must be tested than a variables sampling plan. Okay, and some of the other plans I'll show you too. The other plans, though, get more difficult, and as they get more difficult, they just get ridiculously so. And it's just do the single, and I'll tell you a little bit about that as we go through. So what we're going to need a lot size. So how big's our lot? We're going to need the size of the sample, and this is what Minitab, or if you do hand calculations, which we will not do today because we have software, you'll get back on the sample size and your acceptance number. So you need to provide your AQL and your LQ, and you'll need to provide your alpha and the beta, and you'll get back the size of your sample that you'll need, the accepted number. Okay, and then D would be the number of defective items in the sample, but we won't know that until we pool the sample, right? But if D is less or than or equal to C, so it can be up to C, then we're going to accept our lot. And if it's greater, if D is greater than C, we're going to reject our lot. Okay, so here's an example, and I'm going to do it in Minitab. And if you have Minitab, I just put it right here for you so you can kind of do it yourself, in your downtime. But let me go ahead and I'll pull up Minitab real quick and show you. What we'll do is we'll just go into Stat, and then we'll go into Quality Tools, and then we'll go over to Acceptance Sampling by Attributes, which is way down here. Here's variables. We'll look at this next month, but here's attributes, okay? And let's go ahead and create. We have two choices here. We can create a sampling plan, or we can compare. And we'll compare some next, but let's go ahead and create one. And we're going to do a go, no go. You also have the option of putting in number of defects, okay? But we'll call it a go, no go defective, okay? Units for quality levels. I'm going to choose, you have some choices here. I'm going to choose % defective. We could do proportion, which is kind of the same, or defectives. Per million, we could do that, but let's do % defective, okay? Our acceptable quality limit, it's at 1.5. I'm going to leave it at that. The RQLs right here, it's going to be 10%. This is a percent. These are both percents. And again, these are decided before you put them in, right? But these are just the defaults. So we'll just go with the defaults. As I was saying, in the pharmaceutical, medical industries, this is much too high. One's probably as high as you'll ever want to go. I think when you have pharmaceuticals, you can go as low as, 0.25%. I think 0.65 is usually, that's kind of like a Goldilocks, not too bad, not too good, just right kind of thing. But it really depends on what you're looking at, the risk levels, things like that. So here we have our alpha, which is our producer's risk, and then we're going to set that, we're going to keep that at 0.05. Consumer's risk, which is that beta, we're going to leave it at 0.10. These are, again, percentages, but they're written as percentages here, which is confusing. And let's say our lot size is 5,000. We'll just leave it at this, okay? I'll hit OK. All right, so here's what we have. So for each of these are labels. So we had, the example was that labels are manufactured in plates in lots of 5,000. And so we wanted to implement a sampling plan with all the criteria that we just had there. AQL of 1.5%, because it's labels. We don't really care too much. We might if they're going to go on a pharmaceutical product, but say they're not, and the RQL, we're going to have at 10%. Okay, so what we have here, and hopefully it's large enough. I think I leave it up here. All right, so we have the measurement type here, and then here's just the information we put in. And it uses a binomial distribution to calculate the probability of acceptance. I'm not going to go into that today, but think of it as like flipping a coin a lot of times. Go, no, go. One heads, tails, but it's just go, no, go. Yes, no. Okay. Some of these sampling plans use something called a hypergeometric, and that's whenever you have replacement. This is going to be without replacement, right? Once we pull it from the sample, we're not looking at it again. Sometimes you'll sample things with replacement, and that's when you use the hypergeometric. So that's the difference. And Minitab does this for you, so you don't have to know it, but just some information. Okay. Here's our method. Here's what we input. Okay. And here's our plan. Okay, so it's telling us we need a sample size of 52, and we have to have 2 or less to accept our lot of 5,000. Okay, so right here we have our percent defective. Up here, the 1.5, that's the manufacturer, approximately 95% of the time for the producer. So the probability of accepting it is going to be about 0.957. That's right about our 95%, a little, not exactly, but again, we're dealing with probabilities and random things, so we're not going to be exact, but that's, it's pretty good. It's above 0.95, so that's good. Probability of rejecting, a little bit less than 0.05. It's 0.043, but that's good. Here's our AOQ, and the AOQ is average outgoing quality, in case you forgot, and it represents the average quality of the lot after the additional inspection and rework if we have to rework. Okay, so this is what we have. These 3 columns are what we have on the original lot. But say we, well, I should tell you down here, this is the consumer's part here, 10, right? We were allowing that beta to be 10. And the probability of them accepting is 0.097, which is right around a little bit less, but that's okay for the consumer. We're not overshooting, right? Probability of rejecting is about 0.903 if it's over our limit. That we had set. And okay, so these AOQ and this ATI are if you have to do the rectifying inspection. So when we reject the lot because we went over 2 defectives, they're usually subjected to the 100% inspection. And then we're going to, of course, replace and rework items as we go through it. This type of inspection is called rectifying inspection. And the average outgoing quality here represents the average quality percent, okay, of the lot after the additional inspection and rework. Okay, the AOQ level here is 1.4% or so defective. At that AQL here of this 0.957% defective. Okay, and the average outgoing quality limit is 0.2603 right here. This is the worst it can get. Okay, and represents that, yes, the worst outgoing quality level. Okay, at 4.3% defective. Okay, so this is as worse as the worst it can get. Okay, and if we have a rectifying inspection right here, the rectifying inspection, this is kind of where it gets confusing to people, because you're going, well, wait a minute, there's 5,000 items in this lot, right? But this average total inspection, this is the ATI, this represents the average number of inspected items after the additional inspection and rework for incoming lots with different percent defectives under this sampling plan, right? So if we were to look at every lot that comes through 5,000, and we're pulling 52 items, and we're looking at 2 of them. Okay, this is what we would expect over time. Okay, the ATI per lot represents that average number of labels, that's what we're looking at, or units, inspected at a particular quality level and the probability of acceptance that we set. Okay, so we have this quality level, the AQL is 1.5% defective. The average total number of labels inspected per lot over time is going to be 266.2. And for the quality level of 10% on the consumer's end, the average total number of labels inspected per lot is going to be the 4,521.9. Okay, so as I was saying, these numbers show the ATI curve along with other percent defectives from 0 to 20% down here. Right here. Okay, here's our ATI and here's our AOQ. Okay, so some lots are going to pass with the sampling plan and only have 52 items inspected. Okay, but others will not pass, and they're going to require replacement of the defective items and 100% inspection. So the ATI is the average of these scenarios over time. Okay, so but you can see here. If you over time, if you have like about 5% inspection, you're probably going to need to sample a little bit under 3,000. Oh, and look, it gives you all these different little numbers here. So you have all your, on the left table, you have your lot percent defective, different values up to 20. And then you have your average total inspection over time. So if you look at that top number there, I can't go up to it or it'll disappear. Darn it. And then when I have such a hard time hovering over it. There it is. Oh, where'd it go? Well, if you have Minitab, you can hover over it. It does this to me. It's like, oh, come on, where are you? And if we look at the very top, there's our AQL, 0.015, okay, 1.5%. And there's our inspection, 52. Really, it's a little over 52. Maybe it should be 53, but I said 52, so we'll stick with that. It's, it's just being way precise to those 4 decimal places. But then you can also see as your lot percent defective goes up, there's how much your average total inspection would be. Okay. So again, since we're random sampling, sometimes you're going to pass, sometimes you're not, and you never know the truth, right? Because we're only looking at 52 items in each lot. So there might be times when, oh my gosh, you're going to have a lot, you're going to have more defectives in there, right? But you don't see them, you missed them somehow, and that's the nature of it. Okay. Any questions on these? Let's see, I do have a couple questions here. Oh, let's see. Oh, Charles, thank you for asking all these questions. This is great. Does lot sampling assume all lot sizes went through the same transportation, safety, etc. issues? Otherwise, some lots might have more issues than the others in reality. Absolutely. These are assumptions you're making. And that's why I said sometimes you'll have different sampling plans, maybe for different facilities, different areas, even in the same facility, things like that, different transportation. All these things need to be taken into account. Absolutely. Charles also wants to know, would you recommend with smaller samples like 52 to do it manually? And what if the statistical results differ from physical checks in terms of defect outputs? Well, you would sample to 52, but you need to have a sampling plan kind of to know how many of those out of the 52 you're going to have that are defective. Alrighty, let's move on. Okay, so now let's compare some operating curves. Okay, and you can do this also in Minitab. So let's go ahead and go back into our Minitab screen here. All right, so I'm going to go back into the stat, and I'm going to go into the quality tools, and I am going to do acceptance by attributes again. And now I'm going to compare user-defined sampling plans. That's going to be up here. Okay, in the measurement type, I'm still want to be the go, no go. Okay, but like I showed you, had the different options. We're still going to go with percent defective, and I'm going to use the same AQL and the same RQL. Okay, but now I want to look at some different sample sizes. So, I already put it in there. I put in 30, 52, and 75. Remember, we had 52 before. okay, from our original sampling plan. So I'm just going to look, oh, if we sampled a little lower or a little bit higher, how would that do? And then let's say we allowed for different acceptance numbers, okay? 2 is what we use, but let's look at a 1 and a 3 and just see how it goes. And our lot size is the same, right? We're going the same lot size. You can only do about 3 of these at a time, so you can't put a whole ton of numbers. Unfortunately, I think I don't think it, I think it hasn't changed, but Minitab usually only allows you to look at 3 scenarios or so at a time. But let's go ahead and look and see. Okay, same kind of information. I'm not going to go through it all. You can look at, it's the same information as what we just went through. So just use that handout that I attached. And you can go ahead and read through all of this. But so here's our different scenarios. There's with 30 sample size, and with the acceptance of 1, 52 with 2. Oh, it did it this way. Okay, so it didn't look at like 30 with 2 or 30 with 3. So you'll have to put them in differently. Okay, but here's our probability of rejecting and our probability of accepting. Okay. And the producers are on the top and the consumers are on the bottom. Okay, so boy, right here, ooh, they have a pretty high probability of accepting here. A very high, here's our probability of rejecting, about 80%. Here's our 52 and 2s right here. Okay, so you can see it's a little different here. It's like 0.07. You're going to reject more on the producer side if you have the 30 and 1. Okay, and you're going to reject less on the consumer side, about 10% less if you do the 31. Okay, and then down here, if we have 75 and 3, we're going to reject much less here, because we're pulling a bigger sample and we're accepting 3 now instead of 2. So that's going to make it a little tighter, right, for us. And of course, now you're sampling 75, right? So your manager or you might say, oh, that's too many. We're willing to accept this. These are very close, right? But if I happen to go up to 75, boy, I could tighten these things. I could accept it more on a producer side, right? I could be more sure that the lot's in good condition, right? And also, it's really benefits the consumer too, because now, boy, right at 95%. Okay, and then over time, you would have to sample less. So that would be good too. Again, time and money. Statistics is always about time and money. Okay, and then here we have our different average outgoing quality limits at these different values. 3, this 30 and 1 would definitely be gone. We won't, no way would that work for this 5.2, right? And of course, the 75 and 3 would be better, but then that's going to cost you more time and money. Okay, so yeah, you can use these to compare too, which is great. All righty, now let's look at 0 defects. Oh, let's see, I have another question. Which lot favors the producers and which one favor the consumers? If the lots are more subdivided such that the percentages rejections are lowered, than having bigger lots where percentages are, okay, I think I just answered that, right, Charles? So yeah, so I just read this a little bit too soon or too late. But definitely, you pull a bigger sample and you're saying you're going to be looking at more, right? If you pull a smaller sample, you're not going to be looking as much, so it's a risk, definitely, to the consumer. Maybe not so much a risk to the producer because you're going to get away with more, right? You're going to be, oh, I just pulled a sample of 25 and I only, as long as I have, maybe 3 defective or 2 defective, then, I'm pulling a smaller sample. So what are my chances of seeing the defectives that are in there? Less. Right, less probability. If I pull a bigger sample, that's going to cost the producer more money, but it'll be more beneficial to the consumer because you're taking a better look. And sometimes producers and consumers, that's why they get together and kind of decide on these things. But there's outgoing inspection, right, that the producers might do, and there's an incoming inspection that the consumers will do, right? And so they might have different criteria where the producer will go, hey, this looks good to us, and they send it off, and the consumer goes, no, our criteria didn't meet it, and they send it back. That's why you kind of want to get together and come to these decisions between both parties before you do these sampling plans, right? Okay, so and there's our example that we just did, and there's a screen on it. So let's look at 0 defects. Things to consider. We can do this where we have 0 on a sampling plan. C equals 0 does not guarantee 0 defects, right? It just means you saw 0 defects, okay? And it's not a tool to drive a process to 0 defects. All you achieve is rejection of more products and lots, okay? 0 defects can only be achieved by eliminating the problems that cause the defects, not by sampling. So the problems are in the process. Harold Dodge, a great quality management dude, said quality can't be inspected into a product. Boy, is that true. So people might try to do different things with the sampling plans, but really you need to be careful about that, because if you have bad quality, you have bad quality, and no amount of sampling or statistics or whatever is going to really help you with that. Here's some problems I have. Okay. I would rather at least have sample for 1 defect. Okay, not 0 defects. The C0 sampling plans, they use too small of a sample to test and accept a lot, and that's the other thing. They use a much smaller sample, right? And going for 0 defects with a smaller sample. Using a plan with an accept number of 0 will make you, in the long run, it's going to make you pull more samples. Okay, sometimes we must use the C equals 0 plan. For instance, if you're required to reject an entire lot if only 1 defect is found, then you need to use the C equals 0. If something's going to really hurt somebody, if it's defective in that lot, yeah, then you kind of need to use that. Or if you have excellent quality, okay, and rarely have a defective, then it might be useful. Okay, it's going to allow you to pull that smaller sample. So if you have a process that's in place and you rarely have a defective, then you might be okay with it. Okay, and there are typical types of defects. I have here that for non-critical defects, the non-zero defects plan with an equivalent TPDD and a slightly higher AQL might be okay. Okay, so we have to be aware of these costs of implementing such a plan versus the cost of releasing a critical defect. Okay, the safety again of the customer, of the patient, and such must be an important consideration. And we have different defect types, three main ones. They might be different in your organization, but there's minor, and minor is a discrepancy from the standards, but one that's not likely to affect the usability of a unit. Okay, we also have a major. It's one that's likely to create failure of the unit for its intended purpose. And then we have critical, and that's the one that's deemed to be hazardous or unsafe, and it's dangerous to use, right? So don't do that, right? Yes, you can get away with a smaller sample size as long as you don't have any defects. But if you find a defect, what are you going to do? You have to rectify, right? So you have to look at everything, and you have to replace all your defective units as you go through. So this might be more useful if you have smaller lots. Also, I would think if you have a lot of 5,000, you're almost bound, to have one in there somewhere. But of course, if you're pulling a smaller sample, say you're pulling, 20, you have a lot of 5,000, and say, you're pulling 25 from it. Oh my gosh, what aren't you looking at, right? Are you really getting a good look at that lot? And even though it's random, and it's still, boy, you're kind of setting up the odds in your favor. So that's the reason I don't care for them. So here we can see that the C equals 0 plan is very similar to a C equals 1 plan for a similar LTPD, but the C equals 1 plan allows for a higher AQL. Okay, so see this, the P for the probability of acceptance. Okay, so here's the 0. Here's at 95. Okay, here's our AQL, and here's our probability right here. It's 10%. My gosh, look at it here, right? The same probability acceptance, okay, and the same AQL. Wow, now it's 41. So yeah, your probability of acceptance is much higher when you're allowing for 1 defect, right? You're like, that's very good for the producer. Okay, so as I'm saying, the probability of acceptance is much higher for that C equals 1 plan, but of course we need to pull a bigger sample too. But that could be a good thing for the extra assurance that the sample reflects the true number of defectives, okay? And if the lot truly has no defectives, then we'd accept the lot anyway under C equals 1, right? Because there would be no defectives, right? So yes, we have to pull more. Here we have to pull a sample of 85, and we allow for 1 defective. Here we pull a sample of 50 and allow for 0 defectives. But I'm telling you, you're probably going to fail this more times. So pull the bigger sample. I think in the long run, that's what I think. Okay, but of course you might think differently. Okay, so do we have time to walk through this? It's basically the same thing. Here we're going to use a hypergeometric distribution, but that's the only difference. So what I would say here is, I won't go through it all because we're running short on time, but here for our AQL, Minitab doesn't let you put in 0 for our C0 plan. So we have to enter a very, very small value, such as a 0.05. Okay, and that's the only difference. And I have here a note. Even though the AQL is not required for a C equals 0 plan, Minitab requires something. Okay, so, and you're not going to put in 1.5 because you don't want any defectives, right? You're allowing for no defectives. So you have to put in something small. Okay, that's the only difference. Okay, and so here's an output with it. So I have right here, so you would read this all the same way as in the little handout. But according to the sampling plan we have here, we only need to sample 30 and at 0, right? So if we find one defective, oh boy, we have to go back and look at everything, all 2,500, right? So we only need to sample 30, but we better be sure we don't have any defectives. Otherwise, we have to go back and look at them all. So we want to hope they all pass inspection. So I like allowing us to have one and setting our sample size a little higher. Okay. Okay, so now we have these military standards, and I kind of already covered that a bit early on. The extent of FDA recognition is to use the use of all single, double, multiple sampling plans according to the standard switching rules, which we'll look in a minute, and our acceptable quality limits. So let's go ahead and look at this. We need to know 5 things. This is the ANSI standard to Z1.4 that's based on the military 105E. Now we need to know our lot size, which we always will. Inspection level, single, double, or multiple sampling. We'll look at single. Our lot acceptance history would be good to know in our AQL. Okay, we don't need to specify the LQ. Okay, it's essentially an AQL system, and the RQL or the LQ, LTPDs, it's specified explicitly. Okay, we're going to use tables. Let's go ahead and look at this really quick. Here's our steps. I don't have the actual standards on hand. They're proprietary and they cost about 150 each. At least they did when I wrote this. It's probably more now, but I'll present some details and example today. So we have different levels. Okay, we have these G levels here, G1, G2, G3, and then we also have these S levels. Okay, level G1, that's associated with the smallest sample size, is considered a budget option, and it might be the best if you are short on time and dollars and don't particularly require a thorough inspection of the lot. G2s are Goldilocks. This is what's used most. Okay, it's a moderate option. Okay, not too small, not too large. And then we have our G3 right here. That's the tightest standard, and that requires the largest sample size, means more time, more expense. This is whenever something's very, very important. You don't want to hurt anybody that's critical, okay, or close to critical. You know, it's S's, these are special inspections, S1 through S4. And they're typically used for tests that should only be conducted on a relatively small sample of units. We would need the smaller sample sizes, maybe because the testing is destructive, okay, expensive or difficult to perform, or tend to use similar results across all units that are in there. So the S1 to S4 increase in sample size, with S1 the smallest, S4 the largest. If you're going to use these S levels, then you need to detail it in your supplier and inspection documentation with your reasoning as to why. But mostly we'll use these G2s, which I think is what we're going to use today. So our output that we're going to get from these tables are, we're going to get our sample size, how many items we need, you know, to our limit on how many defectives we can find. We're going to get our alpha, we'll get our beta. Okay, default alpha is nominally close to 5%. Beta at the 10% is going to vary depending on our choice of our AQL, our lot size, and our level. Okay, so if we have a level 2 and our AQL of 0.65 and lot sizes of 100 and 1,000, our implied RQL at a percentage acceptance of 10% is going to be 10.9% versus 14.78%. So really these lot sizes make a big difference, right? And that kind of makes sense. You know, you have a smaller lot, you're probably going to see more. And so, you know, the consumer is going to be okay. That's fine, you know, because you looked at most of it. If you have a large lot size, then the consumer is going to want it to be lower, because they're going to say you didn't look at as much. Okay, so here we have an example, and we'll generate with the following criteria. Okay, all of this information. RQL now is an output, no ability to specify, but we're going to compare it these alphas and betas with these. We're going to compare it these probability of acceptances. Okay, so I'm using the military standard tables. Please excuse, they're ugly, I know, but we want to generate a plan with the following criteria. We're going to have an accept AQL, it's going to be 1.5. Our lot size is going to be 2,500, and we're going to have I have this as it's an advertising firm, and they want to inspect our lot of giveaway flashlights. So does the flashlight, how good are they? Are they working or not? Are they going to be good enough? So what we do first is we're going to get this table 1, okay, and we're going to go over here, general inspection levels. We're going to go down to 2. We're going to look over here. What I say our lot size was 2,500, so it's going to be in here. So we go across and we just kind of match them up. So now we're going to go to the next table, and we're going to look for this letter K. Let's see, we have table 2A now we should be in. So that was table 1. Now we have 2A. You can tell I don't use these much anymore. I use the Minitab, right? And this is our single sampling plans for normal inspection. This is a master table. So we determined that we had letter K, okay? And so for letter K, we have right here is our K, and we're going to need a sample size of 125. And we have to go over this far. There's our oop, oop. What'd I do? Okay, here's our letter K. Sample size 125. We want to look at our AQL now over here of 1.5. So we'll reject. It has a 3 and a 4. We're allowed to have 3 or 4 in here. So we're going to reject if we have more than 5 defective. 3, 4, 5. Okay, and there's our AQL up there. Okay. So our rejection is going to be at 5. Yeah, okay, so this says 1, 2, 3. That's 5 and 6. So we're going to be at 5. That's just so hard to see. Okay. Okay, and then we have one final table. Okay, and this is going to give us some numbers. This is going to give us our AQL and our RQL. We don't put them in, it gives it to us. So here's our acceptable quality. Our AQL is 1.5. And this is going to be over time. Okay, and then here's our 95% probability of acceptance. So we're going to have 2.09 as our calculated AQL at 95%. And if we go down here to the 10 for the consumer, RQL is going to be 7.42. Okay, and these are actually in percentage. Okay, so yeah, that's how you would do it that way. But I think Minitab's much easier. And then I also have a link in the references if you want to read the military standards yourself. Okay, so let's look real quick at some of these things. Switching rules. Okay. So we have the ANSI, right? The Z1.4 provides 3 inspection types. We have normal, tightened, and reduced. Okay, normal is our default starting point. Okay, right here, and we're going to move to reduced when an improvement in our lot quality is detected, and we're going to move to tightened when a decrease in lot quality is detected. Okay, and I borrowed this from down here, so you can always go here and look maybe for some more information, which is very nice. But so we start at normal. Okay. Smaller sample size, so that's normal. And for reduced, if 10 consecutive lots pass in normal, okay, then we can move to reduced. Okay, if 1 lot fails reduced inspection, then we're going to come back to normal. Okay, and go back there again. Okay, tightened, that's lower acceptance numbers than normal, so it's steeper OC curves. Okay, operating characteristic curve. So if 2 out of 5 lots fail in normal, then we move to tightened. Okay, and then if 5 consecutive lots of the next 10 pass, then we can move back to normal. So these are our switching rules. So you'll use those with the tables. There's advantages and disadvantages to the switching rules. Advantages, we have improved protection during the stationary conditions, which is if your process is in good control, you should be fine. Reduced sample size during periods of good quality when you go to the reduced, right? And they work best with a well-established process that's in good control. Now, the converse of that is that you have bad protection during periods of changing quality. So if you have a process that's up and down, and maybe we'll do a webinar control charts to help with that. But if you have a process that's all over the place, you don't want to do this, okay? Stay entightened. You have no protection against isolated bad quality batches or first batch in a run of bad ones, right? So you don't really have a protection against that. And these are more complex to administer, okay? There's also some rules here. You have to follow the switching rules on the plans. You can't just reduce plans straight out of the gate, right? So that's basically what this is saying. You can't just go to reduced. You need to start at normal and then allow yourself, if you want to go to the reduced. Okay, you can't just start out of the gate with that. And again, these tables can be used for single, double, and multiple sampling plans, which we're not going to go into too much today, but we did the single, okay? Same basic statistical reasoning that we've used, okay? One positive aspect of using more or less only a lot size and a QL is that you don't have to understand all the technical details. The tables help you with it, does it for you. However, completely understanding the anatomy of the table is going to help you prevent mistakes, right? A lot of people go, I just want the steps. I just want the recipe. We need to kind of understand it a little bit, right? Just doing the steps. You need to be able to think about it. Just have a little bit of in-depth thinking about it. And just, I have here, just make sure you're using the correct tables, and it's pretty easy. And oh, here's an online calculator too. So it's in the slides if you want to do that, easy peasy, okay? Double sampling plans. Lots are inspected, and a decision to accept or reject is based on a maximum of 2 samples. So you're going to pull 1 sample, and then you're going to allow yourself a second chance if you don't do so well. For the mature processes with a low % defective, these plans provide equivalent protection with smaller sample sizes, so that's a bonus, right? Let me get my little spotlight back. So here's the pros. Very good or very bad lots will be rejected with less sampling overall. It's more economically favorable if cost of sampling is an issue. Equivalent levels of producer and consumer risk with significantly less samples in the long term, so over time, okay? More complex to administer, of course. Okay, so here's a diagram. Really quick, I'll go over it, but you can read about it in the standards or do some Google is our friend, right? And, if it's a quick question you have, you can always email me. Maybe I know of a reference I can send you, or I can give you a quick answer on. If it's something more detailed, we'll talk, about consulting. But, typically, you guys are my peeps, when you come to my webinars and you're on my mailing list and stuff, so I try to be very helpful. So these double sampling plans. So here we have 2 sampling plans. Our first one, we're going to pull a sample of 60. We're doing a 0 defects. But if we have 4, or if we have over 4, we're done. Well, actually greater than equal to here. So if we have greater than or equal to 4, we're done. We don't even go to the second step. That lot's rejected, okay? But if we have, we don't quite pass, we don't have 0 defects, but we have somewhere between 1 and 3 defects, then we'll go to our second sample. We'll go to a second step. And now we're going to pull a sample of 82, a bigger sample, and we're going to, for all samplings, for both the first and second set, we have to have 3, okay? It has to be less than or equal to 3 to accept, okay? And that's basically what it's saying here. Take 60. Here's our number of defects. If it's 0, yay, we're happy. If it's 1 to 3, we go down to our next step. If it's greater than or equal to 4, we're done, rectifying, okay? But if we have 1 to 3, good, we'll go down in here, pull our 82, look at our total number of defects. If they're less than or equal to 3 for both the first and the second set, then we'll accept. But if they're greater than or equal to 4 for the first and second set, we reject and go to rectifying inspection. So that's basically that. Okay. Not too much difference here between a single and a double. Here's our single, but see, we had to pull a larger sample size right off. Okay. And we allowed for 3. Okay. Well, we ended up 3 overall for the double, right? But we might have been able to get away. Hey, if we had 0 defects out of 60, we would be done. We'd pull a smaller sample. So give or take, right? And here we have our different probabilities of acceptance at our different AQL levels, or our different levels here, okay, for double versus single. It looks like here a single, some are higher over time for probability of acceptance. So it looks like over time, if you stick with the simple or the single, you're going to, well, you do a little better until you get a little bit higher, right? But you're getting up to here. That's pretty bad lots, right? And like I said, these double sampling plans look better, do better on good quality lots. Okay, so that's where they're going to be useful. Okay, multiple sample. This is where my head just blows up. I don't think I've ever used this. Okay. There's some characteristics. I'll let you look at the chart yourself, but some things to tell you because we are running short on time. Hopefully you guys can stay a little longer. If not, I'll get the recording out to you in about a week. Multiple sampling plan involves smaller first samples than a single or double. Okay, multiple sampling plan is comparatively difficult to design and explain and expensive to administer. It involves a higher overhead cost as compared to single and double plans. It involves more record keeping. In theory, multiple sampling may often permit lower total inspection than double sampling for a given degree of protection because of smaller sample sizes required. However, the repeated sampling to get to a winner is like fishing for acceptance, and I don't care for that. So, but there's all the different steps. Okay, and then sequential sampling plan. I don't think I've ever done this. No, yes, I don't think I've ever. This is when you do one piece at a time. Okay, you increase the sample size by one part at a time until the sample becomes large enough and contains sufficient number of defectives to decide intelligently whether to accept or reject that lot. Okay, it's a plan in which the sample size is increased by one part at a time. Boy, is it expensive to administer. I would rather you do a multi-sampling plan than this. And then and its overhead cost is great. And it's seldom used, okay? But I just wanted to let you know it's out there. I don't think I've ever used that one. And skip lot. You can do this if you have a good process that's in control, okay? But basically what you're doing is you're only looking at certain lots, or maybe you're randomly selecting lots from a big bunch of lots and sampling from them. Okay, it's cost saving. However, it should only be used when it's been demonstrated that you have good quality. Okay, you'll design a single sampling plan. Okay, specify all your information. That's your reference. Then you're going to start with a normal lot by lot inspection using that reference plan. And then when you hit a pre-specified number, we'll call it I, of consecutive lots that are accepted, then you can switch to inspecting only a fraction of the lots. And the selection and members of that fraction is done. You can do that at random. Or you'll have some kind of plan. But when a lot's rejected, then you go back to normal inspection, inspecting all your lots. Okay, so this is nice whenever you have a good quality and you're just, hey, all our lots are being accepted. We don't have to look at every single one, but you need to justify it and document it, of course. Okay. I have a couple more things, and they're mostly slides of things about what we have to offer here. Well, look at the slides, darn it. But I do have some events that are upcoming. Join our mailing list. If you want to, you can email me since I can't get my slide to work now, and I will add you to the mailing list. And then you'll know whenever anything's happening. Well, good. We got it done pretty much in the hour and a half. So I will send out slides. I will send out a copy of the recording. I also will post a recording to my YouTube channel and sign up on the YouTube channel and do all that subscribing so you get notified of things. And yeah, thank you all for coming. And I hope you have a good afternoon. And I hope it's been raining here. And I hope the weather's nice for you guys this weekend and hopefully for me too. And hopefully we'll see you next month. Okay. Bye-bye.